Welcome to the third and last session of the 2023 series of the Barcelona Mathematics and Machine Learning Colloquium Series, organized by the University Autónoma of Barcelona, with the aim of gathering together all the Barcelona universities and research centers and sharing this experience with all the people interested from all over the world. As you know, in this series, we want to address these two questions about what are the mathematics behind machine learning and what can it do for us mathematicians. We've done this 3 times a year. It's online, and we have a talk, and today we'll only have a talk because we have some technical issues with the discussion, but we'll try to add some discussion afterwards to this video. Questions are welcome anytime. Send them by email or via the chat, or you can use also the usual methods. And the most important part is who. So we've enjoyed already Mark Lackenby, Liz Manch, and today we finish with Jürgen Jost talk. So he's from Max Planck Institute, and he will talk about generalized curvatures and the geometry of data. And actually, this is something that very recently was posted on the archive, just kind of a year ago. So we look forward to hearing from him. What can geometry can do for this data analysis? So now I will be the one passing the slide. Sorry if that introduces some mismatch between what he's saying and what's on the board.
Just show the slides and I'll start.
Yes, I will do that. Just a second, and I'm just sharing this.
I'm sorry for the technical problems, but I'm not at home and not in my office, so I don't have anybody to help me with those things here.
So please, Jürgen.
Yeah, just if you share the slides, and
yeah,
good. Okay, so I guess I can start, and so it's my pleasure to be able to talk to you, and I thank you for the invitation. Of course, I apologize for the technical problems on whichever side they are. So I will speak about generalized curvatures and the geometry of data. On the next slide, you will see that this is joint work with Pavane Yoharinath, and the next slide will start. So I want to make, first of all, a distinction between topological and geometric data analysis. So topological data analysis asks the questions when balls in a metric space XD intersect. So X is the space and D is the metrics there. And as you know, in TDA, you ask when do the balls intersect. Next. Now, in geometry, you ask a more refined question, namely you ask how much balls have to be enlarged in order to intersect, and that will be an important theme. So topological data analysis is qualitative, but it is in a certain sense quantitative because you have the dependence on the radius of the balls, whereas geometry by its very nature is a quantitative branch of mathematics. And so this quantitative aspect of geometry is captured by a suitable concept of curvature. And that is one of the most profound insights in geometry. And curvature, from the perspectives that I'm using here, quantifies convexity. And global convexity is a property that is characteristic of non-positive curvature, which will be abbreviated as NPC. So why is NPC important? So there are many important spaces that have non-positive curvature. Of course, Euclidean space have 0, therefore also non-positive curvature. Hyperbolic spaces, more interestingly, have negative curvature, constant curvature. Symmetric spaces of non-compact type have non-positive curvature, and if the rank is at least 2, some directions the curvature is 0, and in others it's negative. And then you have also more general spaces, namely metric trees, or more generally Euclidean Brouillard-Titz buildings. And Also in geometry, you often have moduli spaces like those of Riemann surfaces or those of abelian varieties that have been shown to have non-positive curvature. And hyperbolicity is also a general property, as pointed out by Gromov in particular. And according to his scheme, most groups are hyperbolic, and together with their Cayley graphs as geometric objects. So again, a little more about mathematics. I will come to other aspects soon, but in mathematics, you want to understand representations of fundamental groups in order to understand the topology of spaces, and they lead typically to mappings of the underlying space into some space of non-positive curvature, because the corresponding symmetric space is of non-positive curvature. And then, as we will explore, there will be relations with topological concepts like hyperconvexity and topological data analysis. So convexity usually means that the square distance function is at least as convex as in the Euclidean case. And that will be the characteristic property of non-positive curvature. And therefore, if we go from linear analysis in Euclidean space, we can go to convex analysis in non-positively curved spaces, essentially using the same methods, concepts, and ideas. And the characteristic properties that we shall explore here are ball intersection properties. So the slogan will be that balls intersect in non-positively curved spaces at least as easily as in the Euclidean case, although the size of the intersection will be smaller. And although this can be iterated, if you have a space of non-positive curvature, then if you look at an L2 space of mappings from anywhere into a non-positively curved space, then again, this is an NPC space, even though, of course, in general, no longer locally compact. And just one essentially final mathematical aside, it also connects quite well with the regularity properties of partial differential equations, but perhaps I do not go into details here. So now let's go into metric geometry. Let me just recall some preliminaries. We have a metric space with a distance function. And then if you look at a continuous path from unit interval, just for normalization, into the space with some fixed endpoints, then we can define its length, as you learn in your calculus class, by looking at distances between points on the path and takes the supremum then over all such partitions. And then you call the space a length space if the distance between 2 points is equal to the infimum of the length of connecting paths. And the length space is called geodesic. It's not only the infimum, but if it's a minimum, that is, if it can be connected by a shortest curve of smallest length, which then is called the shortest geodesic, so that the length of the curve is equal to the distance between the points. Now, on the next slide, we see we have an important definition, namely we call a point a midpoint if its distance to both points x and y is just 1/2 of the distance between them. Of course, there may or may not exist midpoints, but the important property is that we will use, that we define the condition of midpoints. And so more generally, we look at if you have two balls, for example, of radius equal to 1/2 of the distance between the original points, then if you have a midpoint, then this would be a point of intersection. One can generalize that slightly, take any two radii whose sum is at least equal to the distance between those 2 points, and then you ask that the two balls have a non-empty intersection. The balls are always closed balls that I use, and so the slogan will be then the two balls that can intersect because the radius condition is satisfied, do in fact intersect. That is total convexity. And just as a convention, I will only look at positive radii in the sequel, except at the very end. So now we can formulate that in a somewhat more complicated way. So again, we take two radii, whose sum is at least equal to the distance between the 2 points, which are now called x1 and x2. And then for every point, I look at the distance from the 2 points xi and divide it by the radii, by the corresponding radius. And then I want to find points where this quotient is as small as possible. And then this quantity, the supremum of all radii, is achieved when we have this property that we already had for midpoints, but now in a somewhat more general way, that the distance between x1 and x plus the distance between x2 and x is equal to the distance between x1 and x2. So that you see on the right-hand side in this picture there. Then the balls just touch, but because they're close, they intersect. Now, that is then our aim. We want to find points between 2 points x1 and x2 that makes this quotient as small as possible. In general, we may not be able to achieve that, but then we want to quantify to what extent that can fail. But if we can do it with 2 points, x1 and x2, we may also naturally ask what happens if you have 3 points, x1, x2, and x3. And then it becomes interesting. So far it was rather trivial. So now we come with the first definition, geodesic length space. That is a point, that is a space where the distance between any 2 points can be realized as by the length of a shortest curve between them. Such a point now is called a tripod space. If for any 3 points we find a median point, that is a point that realizes this relation that we have just been looking at for any pair taken out of the 3 points. So the distance between x1 and m and the distance between xj and m, I and j are different, is equal to the distance between xi and xj for all different indices between 1 and 3. And here you see a picture. Of course, this looks like a tree-like structure, and that is what you should think about. But of course, you will directly notice that in general, metric spaces are not tripod spaces. For instance, if you have a Riemannian manifold of non-trivial dimension, then it will not satisfy the tripod property, as you see in this picture here. So the balls intersect pairwise. So medians or midpoints between 2 points are not a problem, but nevertheless, there is no triple intersection, so you don't find a median. That is, of course, a picture in Euclidean space, in the Euclidean plane, but it's similar on other manifolds. But nevertheless, there are examples where this holds. As the picture already indicated, it is satisfied on metric trees, and in general, it is also satisfied on spaces equipped with L-infinity metrics. We will come to that in more detail. And there's a more general class of spaces that will be very important, the so-called hyperconvex spaces, where not only this, but even a stronger property is satisfied, namely where we can take an arbitrary number of points, not just 3. So now our strategy then will be that we define curvature as a deviation from the tripod property. Of course, that leads to a different normalization, but nevertheless, what we want to have, the ideal property is that when we have 3 balls that could intersect, because the sum of two radii is at least equal to the distance between the corresponding centers, do have a non-trivial intersection. These are the tripod spaces, satisfy the slogan 3 balls that can intersect, do intersect. And again, the picture again, it is not satisfied in this picture, but it is satisfied in a tripod, a metric tripod. Again, we can formulate that in a more complicated way. Again, we take points, we look at the distance of those points x from the 3 points x1, x2, and x3, and divide by the corresponding radius. And then we want to find points x for which this relation is as small as possible. And then, of course, we only need to look at radii whose sum is equal to the distance between the corresponding points, and then we just take the supremum over all such radii. And this property that Ri plus Rj, the sum of the radii, is equal to the distances between the two corresponding centers, is solved by the Gromov products. So, in other words, this relation has a unique triple of solutions, R1, R2, and R3, which are just given by the quantity on the right-hand side, which is essentially the extent to which the triangle inequality fails to be an equality. These are the Gromov products. And so therefore, we only need to consider those radii, and then we look at those points for which this quotient dxi divided by x divided by Ri is as small as possible for all 3 points x1, x2, and x3. And we call a point that attains that infimum weighted circumcenter. And it solves an optimization problem in R3 with respect to the L infinity norm, and that is why L infinity metrics will essentially play an important role in the end. Of course, you need to show the existence and uniqueness, but for instance, you can do that in Alexandrov's spaces of non-positive curvature. I will give you a definition in a moment. At the moment, I just want to mention that in spaces that you're naturally interested in, you do have the existence and uniqueness of weighted circumcenters, even though uniqueness will in general no longer hold in L infinity spaces. So now, as I already indicated, then we have this property for 3 points. Of course, we might ask, why don't we have it even for more than 3 points? And so this is a fundamental definition. The metric space XT is called hyperconvex if we now take any family of points and radii centered of balls centered at those points. Again, we require the necessary condition that for any pair of points, the sum of the radii of the balls is at least equal to the distance between those center points. And then we ask that the corresponding family of balls has a non-empty intersection. And if you have a convex metric space, then the radius condition can just be replaced by the condition that the balls intersect pairwise. So, in other words, we ask that whenever balls intersect pairwise, all balls intersect pairwise, then we also have a common intersection. So again, a slogan, now balls that can intersect do intersect. That is hyperconvexity. And of course, hyperconvex spaces are tripod spaces, because for tripod spaces we require only for 3 points. Here we can see some examples. On the upper left, we just have 3 balls in the Euclidean plane. That is not satisfied. The 3 balls intersect pairwise, but they don't have a triple intersection. On the upper right, we have a metric tree that is satisfied. Takes the 3 points, take balls around them that intersect pairwise in the smallest possible way, then they would just intersect in the median between them. And so we have that point. On the lower left, we see the L1 topology of the plane. And in the L1 topology of the plane, you always have this property because the L1 balls are these diamonds here. And we have pairwise intersection, but we also have a triple intersection. But notice that L1 metrics in higher dimension no longer have that property, but L infinity spaces actually do. And on the right-hand side, finally, we have 3 points on a circle, and there the tripod property fails in the most drastic way. So we have pairwise intersection. Let's just go back to the picture. We have pairwise intersections of the balls whenever the radii of the balls are equal to 1/2 of the distance between any 2 of them. But in order to get a triple intersection, you need to double the radii. You only get triple intersection if the radii of the balls are equal to the distance between any 2 of them. And so that is the most drastic way in which the tripod property can fail. Now, these spaces have been introduced already a long time ago by Aronshine and Panich-Bhakti in 1956, and they showed that hyperconvex spaces are complete and contractible to each of their points, so there's no topology there. That will be an important point in a moment. Then there's a dual characterization, namely there's no obstruction to the extension of one Lipschitz maps from a subspace of any metric space Y to X. So if on any subspace of Y you have a one Lipschitz map to X, then it can be extended to a one Lipschitz map to all of Y into the same space X. And then Isbell, and it was rediscovered by Andreas Stress in more general terms, discovered that every metric space is isometrically embedded in a hyperconvex space called its hyperconvex hull. It sits, maybe you know the Kuratowski embedding into an L infinity space, but then in that L infinity space you can find hyperconvex space which is typically smaller, but in which still the metric space is embedded. And so the hyperconvex hull, that embedding space of a compact space, is compact. And if you have to start with a finite space, then its hyperconvex hull is a polyhedral complex. So that naturally then leads us into polyhedral geometry. Now let's look at the relation with topological data analysis. Let me just recall what one does there. You take a metric family that is some points xi with a metric distances d. You take a positive radius, and then one can define a check complex, a simplicial complex that has a Q simplex associated to any tuple of Q plus 1 points for which the corresponding balls of that radius R have a non-empty intersection. And then topological data analysis then takes this R as its single parameter and records how the homology of this complex varies as a function of R. And these are the famous barcodes that you see in applications of TDA, of topological data analysis, that apparently are very insightful for many types of data, metric data. So again, here we have the situation where we have 3 points. These are radii, so they're just part of the metric space. And these 3 points span 3 edges, because the corresponding balls of that radius R do intersect pairwise, but the simplex is not, the triangle is not filled because we don't have a triple intersection. That is how the topological data analysis works. So you need to enlarge the radii of the balls a little bit in order to get a triple intersection. And so this triangle, when it is not filled, gives you a non-trivial one-dimensional cycle. So it contributes to the first Betti number, and this contribution to the first Betti number disappears when you enlarge the radii a bit more. And so that is then the corresponding bar, and the barcode ends. So here we actually see it. Now, so we have enlarged the radii now a little bit so that we get a triple intersection. And then in the check complex, the triangle gets filled. But for computational simplicity in topological data analysis, one often works with the Vietoris-Rips complex, where you always fill simplices whenever you have the boundary edges. So now this is a relation with topological data analysis. In hyperconvex space, all the simplices in the check complex would be filled. That is, whenever you have pairwise intersections, that is, when you have edges between 3 or more points, then you also have a common intersection, and therefore, according to the prescription by which the check complex is built, the corresponding simplex is filled. And you don't have any local homology. And that is the check complex equals the Vietoris-Rips complex for hyperconvex space. So now, of course, hyperconvexity is a rare condition, and we want to be quantitative. So we measure the deviation from hyperconvexity. There are 2 variants. Either you could relax the condition by allowing to enlarge the radii a little bit. That is, not ask that the balls of the radii Ri intersect, but that only the balls of the radii Ri plus some positive delta intersect. That would be delta hyperbolic. Or you could look at a multiplicative factor. You don't ask that the balls of radii Ri vanish again, but you only ask that the balls of radii lambda times Ri, where lambda is, of course, at least 1, do have a non-empty intersection. That is lambda. That is what is called lambda hyperconvexity. Delta hyperbolicity, additive, and lambda hyperconvexity, multiplicative. For a large radii, of course, delta becomes insignificant, and so it's good for asymptotic considerations, in particular in the scheme of Gromov. That is a very natural property, whereas the lambda hyperconvexity is naturally invariant under scaling of the metric D, so it also has its advantages. Now, it turns out, when you look at this lambda hyperconvexity, Hilbert spaces, and in particular Euclidean spaces, are square root of 2 hyperconvex. That is, if you have a collection of balls that intersect pairwise, then you need to enlarge the radii at most by a factor of square root of 2 not to get a common intersection. Reflexive and dual Banach spaces are at least 2 hyperconvex. So they may be a little worse than Hilbert spaces, and the LP spaces, for instance, are 2 hyperconvex. And if X is finite, also the L1 space is 2 hyperconvex. But as I already said, L infinity is always 1 hyperconvex, that is hyperconvex 2 Kur. L infinity spaces are hyperconvex. Now, we want to go into geometry and relate that to curvatures. Now we can use these concepts to compare spaces with each other or with reference spaces like Euclidean spaces. And of course, such a comparison in geometry is quantified by the concept of curvature. Now we have a quantitative notion of comparison, this lambda hyperconvexity, and we want to turn that into a curvature concept. Because from the abstract perspectives that I'm developing here, curvature relates intersection patterns of ball to convexity properties of distance functions. So now I want to recall some classical concept of non-positive curvature. Of course, in the many geometry, you have Riemann's notion of curvature and Riemann's notion of sectional curvature, and you know what non-positive sectional curvature is. And Alexandrov generalized that to so-called cut-zero spaces. These are geodesic spaces. And in the picture on the left-hand side, you see 3 geodesics in such a space. And then you look at a Euclidean comparison triangle. That is, you look at three points in the Euclidean plane whose distance is equal, such that the pairwise distance between any two of them is equal to the distance in your original space, and that is the length of the corresponding geodesic in the space X is equal to the length of the straight line connecting these 2 points in the Euclidean plane. So you see that indicated there, and the non-positive curvature requires that if you take one of the points and if you connect it to the center or to any point on the opposite geodesic, you do the same in the Euclidean comparison triangle, then in the original space, the distance is not larger than what you get in the Euclidean comparison triangle. So in other words, geodesic triangles are typically curved inward in an intuitive sense, as you can see on the picture in cut-zero spaces. So triangles in cut-zero space, in other words, are not thicker than Euclidean triangles with the same side length. That is Alexandrov's definition. There was another important definition by Busemann, developed at about the same time after the Second World War. So a geodesic space XD is a Busemann convex space if for every 2 geodesics that start at the same point, the distance function on these geodesics is a convex function of the arc length parameter. So that just means that geodesics in Busemann space diverge at least as fast as in Euclidean space. And for example, you all know there's some good intuition of the geometry of hyperbolic space, and there you see that geodesics diverge exponentially as opposed to linearly in Euclidean space. So clearly they are Busemann non-positively curved. And it turns out that every cut-zero space, every Alexandrov space of non-positive curvature also has Busemann non-positive curvature, but the converse doesn't hold. The Busemann's condition is more general. So now we come to our definition. In our sense, the space has non-positive curvature if for each triple of points, again, we use a comparison triangle in the Euclidean space. So the distance between x1i, x bar I, and x bar j is equal to the distance between xi and xj in our original space. And then we look at quantity that quantifies the deviation from the median property in our space is not larger than this corresponding property in the Euclidean space. In other words, if we have 3 balls that intersect pairwise, takes the same configuration Euclidean space, then in our original space, we know that we need not enlarge them anymore, then we would have to enlarge them in the Euclidean comparison space to get the triple intersection. So we get the triple intersection at least as easily as in Euclidean space at least as easily mean that the factor lambda, by which we have to enlarge the radii, is not larger than we would see in Euclidean space. So here are again the definitions. So rho defined in our original space, this quotient dxi comma x divided by ri with respect to all 3 points. Then you find one x for which this is as small as possible. Then you look at the corresponding quantity in Euclidean space. Of course, I just take Euclidean distances and you can take the minimum. And what you have in the original space is not larger than what you have in the Euclidean plane. For the circumcenter, as one might call this point x, is at least as close to the vertices x1, x2, and x3 as it would be in the Euclidean case. So, in other words, when we have any triple of closed balls with pairwise intersection, and then when we enlarge the factor, the radii by a factor rho, then we are sure to get a non-trivial intersection whenever the corresponding configuration is the same enlargement factor rho as the common point. So to repeat, balls do not need to be enlarged more than in Euclidean's case, in the Euclidean case, to get a triple intersection. That is our definition of non-positive curvature. Of course, the question then is how it relates to other conditions of non-positive curvature, those that I have sketched already. First of all, the tripod spaces, of course, have non-positive curvature because the enlargement factor is the smallest one, I equal to 1, because we already get the triple intersection from pairwise ones. Now, complete spaces, Alexandrov space of non-positive curvature have non-positive curvature in our sense. The converse is not true because our spaces need not be geodesic, nor need geodesics be unique. In fact, L-infinity spaces are a good example. Their geodesics, shortest curves between 2 points in general are not unique, but nevertheless you have the tripod property and even the hyperconvexity. But this would not be compatible with Alexandrov's definition. And importantly, with a view towards analysis of data sets are always finite, and so the approximate versions, delta hyperbolicity or lambda hyperconvexity, naturally apply to discrete spaces. And it connects, of course, well with Riemannian geometry. So complete Riemannian manifold has non-positive curvature in our sense if it has non-positive sectional curvature in Riemann's sense. Of course, the same is true for Alexandrov spaces. A complete Riemannian manifold satisfies Alexandrov's, or in fact Busemann's condition of non-positive curvature if and only if it has non-positive sectional curvature. So just briefly, maybe I go over the sketch of the proof because the time is advanced already and we directly go to the next slide. Now we can derive a couple of conclusions. For the moment, there will be a little more after the conclusion. So the check construction that I've been talking about in general, more generally, assigns to a cover of a space X a simplicial complex. This vertex set, the index set of the cover, and a simplex sigma j whenever the corresponding sets in the covering have a non-empty intersection. And when all intersections are contractible, that is the usual property that one imposes in topology, the homology of the simplicial complex equals the homology of the space X under some rather mild conditions. And in particular, when our space is a metric space, we can use covers by distance balls, corresponding constructs a check complex, as I've already indicated, and then that simplicial complex has its check homology, and that is equal to the homology of X. Now, again, to recall, when our metric space happens to be a hyperconvex space, and again, we cover it by distance balls, then whenever we have non-empty intersections for some part of the index set, for some parts of the index sets, then we also get full intersections. That is, whenever the simplicial complex contains all the boundary facets of some simplex, it also contains that simplex itself. And so therefore, there are no holes, and there are correspondingly no local homology groups. So that is really the point here. Hyperconvexity is equivalent to no local homology from the check construction, check covering with distance balls. Now, when we only require lambda hyperconvexity for some factor lambda that is bigger than 1, then, of course, non-trivial homology groups may arise. And now, the conclusion is that from the perspectives that I have developed here, hyperconvex spaces are the simplest model spaces, and homology then can be seen as a topological measure for the deviation from such a model space. So homology groups, of course, lead to Betti numbers as integer invariance, and that is again exploited powerfully in topological data analysis. But as I already said in the beginning, geometry can provide more refined real-valued invariance, and thus these Betti numbers as integer invariance. And after Riemann, after the fundamental work of Riemann 150 years ago, the fundamental geometric invariants are curvatures. And in our framework, now the essential geometric content of curvature can be extracted for general metric spaces, no longer depends on infinitesimal differential calculus. And the basic class of model spaces for curvature now, from the perspectives that I am developing here, is a class of tripod spaces. And this is a special class that in particular contains the hyperconvex spaces that have even better properties than arbitrary tripod spaces. And so from that perspective, the geometric content of curvature in this abstract setting is a deviation from the tripod condition. So it's a very simple formulation of the geometric content of curvature. And now, of course, the Euclidean spaces only have a subsidiary role based on the normalization of curvature that assigns the value 0 to them traditionally. But that is kind of arbitrary. It's important. So traditionally in geometry, you have the Euclidean space in the middle, and then you divide the class of space into those that have non-positive curvature and those that have non-negative curvature. But from perspective here, we have a one-sided perspective. That is, we look at the extreme spaces, the tripod or the tripod spaces or the hyperconvex spaces, and then we just check the deviation in one direction, that is with that parameter lambda from those spaces. So now the final point I want to make here. This allows us to translate geometry into topology with the following construction. Well, let's carefully go through the slide. We have a metric space XD as always. So now we construct a simplicial complex X check, whose vertex set consists of pairs of points and radii that now are also allowed to be 0 if you want to. And for every finite index set with more than 2 points, we let xi, ri be a set of vertices with all the ri being positive and different points xi. And then, according to what we have done before, we let x check carry a simplex whenever these corresponding balls have a non-empty intersection. So this now is a simplicial complex whose topology incorporates the geometry of the underlying metric space. So the important point of geometry of metric spaces, of course, is that the geometry is not really just captured by looking at pairwise distances. It is captured by looking at relations of distances between more than 2 points, and to the extent that the triangle inequalities fail to be equalities. And that is captured here. So in particular, it generalizes the concept of the Gromov products here. And so this is a simplicial complex that we propose as a model for topologizing the geometry of a metric space. And of course, if we take the radii to be constant, then we are back to topological data analysis. So we can look at all the slices with constant r, and then we are in topological data analysis. But of course, in general, we can look at situations where the radii vary from one region of the space to another region. For example, the data may not be uniformly distributed. They may cluster somewhere, and there maybe we want to look at smaller radii, and they may be sparser somewhere else, and there it may suffice to just look at larger radii. But we can handle that flexibly here. This is general definition. So now one can explore some questions. From the perspective of analysis, one can look at the regularity for maps into such spaces. That is close to my earlier work because I've been looking at the regularity of generalized harmonic maps into spaces of non-positive curvature in the sense of Alexandrov. Perhaps for you, more interestingly, that should give new schemes for geometric data analysis. One can use that. We are using that also to explore the asymptotic geometry of networks together with Arijit Samal, the head of our partner group in Chennai in India. And again, maybe one remark here, non-positive curvature, as already conceived by Gromov, is really a large-scale property. It is an asymptotic property that tells you something about how the space behaves at large. And therefore, if you look at these concepts to explore the geometry of networks, and locally they don't tell you very much. Locally, a network looks like a tree, but asymptotically, of course, it may be quite important to distinguish networks with different such curvature properties. Just look at infrastructural network, road networks. If you have 3 cities, then of course you can just build 3 roads connecting any pair of cities, but alternatively, you could also look at some point in between, some kind of median, and just connect every city with that median. That may increase the travel time, but it may save you expenses for building roads. And so that is an intuitive exploration of these curvature concepts for infrastructure networks. And then, of course, we can ask more generally for the geometry of hyperconvex and tripod spaces and their variants and generalizations. If you enlarge the lambda, how does the geometry change, and so on. And so now I'm at the end of my presentation. Just give you some references. So as I said, this represents joint work with Parvane Yoharinat. You have some papers there, and now we have also completed a monograph where this is systematically incorporated. That will appear later this year in the new book series, Mathematics of Data, which I'm also editing. So with that, I can thank you for your attention, and I'm sorry for the technical problems. Now we need to see how we can organize a question session. If there are any, probably I can see when you put questions in the chat, or you may also maybe want to write them to me by email or whatever.
Okay, so thank you. Thanks a lot. And
with great pleasure.
Yeah, and let's try some question time. So yeah, even though I feel a bit
okay, just put questions in the chat and then share your screen.
Yeah. So yeah, actually, I would start with I've written some here, and everyone is welcome to write in the chat, and then we can.
Yes, that is of course very good question. So one, as I said, is to explore the geometry of networks, infrastructural networks, to explore to what extent, for example, a road network is designed according to minimizing traveling distance, or whether it's designed in order to minimize road lengths. Now that would be one application. The other one would naturally be to look at the data sets and as in topological data analysis, but let the radii vary according to the corresponding density of points. Yeah, and then of course we also want to relate it to other schemes like manifold learning and UMAP and so on, whichever schemes you have for data analysis, and that is something that we are currently systematically exploring.
Okay, thank you. I have another question where you can see applications of what you have developed beyond data analysis, especially in math.
Yes, I see applications, and in fact that was, since my background is in pure mathematics, that was somehow at least my motivation to understand curvature from a perspective that is as abstract as possible. Yeah, and then of course so far I've explored that for 3 points. And in Riemannian geometry, of course, you know that sectional curvatures give you a complete set of local invariants. That was one of the basic discoveries of Riemann. Now we can ask for other metric spaces. How many points do you actually need to consider in general to completely characterize a metric space? Or which metric spaces can be characterized by just looking at these relations for 3 points? When do you need 4 points, but 4 points suffice? And when do you need more points? So that would be some kind of general classification of metric spaces according to the difficulties of the intersection patterns of balls that you need to consider in order to completely characterize the metric relations in such points, in such spaces.
Okay, thank you. And I also wanted to ask, how did you start working on this area?
Well, it came about from many perspectives. Many years ago, I was interested in the geometry of non-positively curved spaces, because these spaces arise very naturally in geometry when you look at representations of fundamental groups in Lie groups over non-Archimedean fields. So that was, of course, very different motivation. And then I developed a general theory of harmonic mappings into such spaces, proved the existence and regularity of those, and that then leads to applications in, for example, in order to understand fundamental groups of Kähler manifolds. But being a pure mathematician, it was a natural desire for me to view all of this from a more abstract or more general perspective. And then when I got together with Pavane, we started to realize these concepts quite naturally fit the schemes that are used in data analysis. So we were driven into that field, and so then we also Andreas Dress, whom I mentioned earlier, is a very good friend of mine, and he also looked at the hyperconvex hulls of finite metric spaces and explored their geometry as polyhedral complexes, but then naturally questions arise about hyperconvex hulls of other spaces, for example, in the work of Facundo Memoli in Ohio, and I've been discussing those with him and with former students of mine, and so now we are also trying to explicitly characterize the hyperconvex hulls of other non-finite metric spaces, which appears to be quite difficult, actually. So it leads to many questions in geometry, and we are branching now off into several directions, from applied data analysis of networks to questions about geometry of hyperconvex spaces. So we are now also with others actively researching some of these questions.
Thank you. And perhaps a last question, unless someone else has another one. Do you expect geometric data analysis to become?
Yes, I would think so, because TDA somehow, I think, has essentially explored its possibilities. Of course, you can ever apply it to other data sets that you have not studied yet. But I think if you want to identify some finer property than just those barcodes that you have there, then just some topology, then you need more refined geometric perspectives that I've been trying to develop. So my answer to that question simply is yes.
Okay, glad to hear that. So if there are no more questions on the chat, so I would just say, well, thanks a lot for
thank you for your attention. It was a great pleasure for me, and I apologize for the technical problems, but I'm neither at home nor in my office. I'm now I'm also a PI in an artificial intelligence scheme, and I'm in their labs. And of course, if you work with AI, then computers never really work.
Okay, thanks a lot. Yeah, thank you so much for accepting the invitation, talking to us. Okay.
Thank you very much again, and of course I hope to meet you sometime in person in Barcelona or whatever.
Sure.
And so
you are most welcome to
without any technical problems.
Yeah, sure. Yeah. The in-person version of this talk, an advanced talk. Okay, thanks a lot. Bye-bye.
It's a great pleasure.